All right, problem number 3. This one, it says the graph of an equation is given. So we can kind of see that image here. We want to find the intercepts, and then we want to indicate whether the graph is symmetric with respect to the x-axis, y-axis, or origin. So I'm going to need to give you a few notes here. I will point you to the textbook so you can see the formal definition. So if you go question help, view textbook, I've already opened it. I have a tab down here, and I'm just going to kind of show you where they are. So this is page 162. Here's a formal definition. You're given an ordered pair. If for every ordered pair you have, if you were to change the x value negative and the y value stays the same, so kind of like here you have a positive xy, and if I flip negative, I still have the same y value straight across. It's a flip across the y-axis. That's y-axis symmetry. Up above it, we have x-axis symmetry, which is very similar. You have every point x, y. If you make y negative this time, so you have a positive point, you make the y value negative, you come below, you have that same point on the graph with the x coordinate being the same and y being positive or negative, then it is symmetric with respect to the x-axis. Tongue twister. And then with the origin, so you would have every ordered pair x, y. If you change both x and y negative, then it's respect to the origin. Has symmetry with respect to the origin. And then if I go over one more page, I believe it says test for symmetry. So all the simple thing that you need to remember for x-axis, you replace the y with the negative, and if that point's on there, then you have x-axis symmetry. With the y-axis, you make the x negative. So kind of like the ordered pairs, you do the opposite one. Origin, you make them both. All right, let me show you what this looks like in function format, and then we will answer this problem. All right, so x-axis symmetry. Okay, no special name, but we'll be using function notation, so f of x. And remember, you made the y value negative, so this whole thing represents y, so I will make this negative on the outside. So if you have a function, you put the negative on the outside, which is the y value. Graphically, just give you a little image. Okay, this is the y-axis, this is the x-axis. And we want x-axis symmetry. So I'm going to do a parabola on its side, and I'm just going to show that if I had this point up here, let's call it positive 2, 3, I would have a mirror image right across, and we would call that positive 2, negative 3. So it's like going right 2 and up 3, right 2, down 3. So this is x-axis symmetry. No special name. This is it. All right, now we also have y-axis symmetry. I guess I can put this order pair here. What it looks like, you have an order pair x, y. This also help. Then if you have x comma negative y, that's what that means. Okay. All right, now y-axis symmetry. It is also called even. Very important to know that. All right. So y-axis symmetry has a special nickname. They call it even. So function notation wise, you will see f of x, and then if that's equal to f of negative x, which means you make the x value negative, the y value would be the same, then those are symmetric with the y-axis, or they are called even. As far as ordered pairs are concerned, you would have ordered pair xy, which is equal to negative xy. All right, what a little image looks like of that. I'll just do a traditional parabola. And let's say I had the ordered pair let's just say that this is the ordered pair -3, +2. Alright, right across the y-axis this time, we would have the same ordered pair, but this time the x value will be +3, 2. So if you take the ordered pair, the y values are the same, the x values are changed from positive to negative. This is y-axis symmetry, or otherwise called even. Alright, and then the last one is origin symmetry. It is also called odd. Now be careful, I don't know that mathematicians have made these terms to be confusing, but they can be. Just because a graph is even or has y-axis symmetry does not rule it out from being odd. Okay, so you can have a graph that is even and odd. Okay, which sounds weird because normally when we deal with numbers, this number 2 is even, it is not odd. Okay, and this number 3 is odd, and therefore it's not even. They cannot be the same, even and odd. But with graphs, it can be. Okay, and I will try to show you an image of that. Origin symmetry, function notation says if I take the negative f of x and it is equal to f of negative x. So you're making both x and y negative, and they come out to be the same, then it is odd. And ordered pairwise, we have x, y. That would be equal to -x, -y, as if you took both of them and changed them. Origin symmetry, let's just use the graph y equals x. I can use x cubed. So it would be similar to if you took this graph and flipped it across the y-axis and made the y negative, you would get this dotted line if you flipped it across the y-axis. And then if you took that image you flipped across the y-axis and then flip it across the x-axis and it flipped down, you would get this image. So it's essentially making x negative and then making y negative, or vice versa. If you made the y negative first, if you flipped it across the x, it would look like this. And then you flip it across the y. You can do either one first. All right, but you would have some point, let's just call this +1, +1. And then you would, over here, you have another point, mirror image across this diagonal, -1, -1. So that's what origin looks like. Now let me show you that you can have any one, 2, or all 3 of these, possibly. I don't know if you can have every pair, just offhand thinking about it, but we can graph a circle. So if I graph the circle, all right. This circle, as you can see, if you were to flip it across the y-axis, it's a mirror image. If you flip it across the x-axis, it's a mirror image. And kind of like what I just showed you here, if you flip this across the x and then the y, you have that same image in the opposite corner. So this graph would have all 3 symmetries. It would be x-axis, it would be called even, or y-axis. It could also be called odd, or origin. So this graph of a circle would have all 3 symmetries. That's just one example that has all 3. Okay, now that we have the notes and an idea of what's going on, we can answer this question. So looking at this graph, we want to first find the intercepts. So where does this graph cross the x and or y axis? Still kind of hard to see, but it looks like, if this is counting by 1, 2, 3, 4, that looks like +5 and -5. Looks like a complete mirror image. So we have intercepts of -5, 0, -5, 0, and then comma +5, 0. Don't have any y-intercepts. There's no part of this graph crossing the y-axis. Intercepts are, use a comma, so they look good. Okay. And now we want to determine, does this graph symmetric to the origin, x-axis, or y-axis? All right, so just from the appearance, okay, of this graph, just from the appearance, you can see that this is the y-axis, and this looks to have a mirror image. Now, we can't check it mathematically, but we can look at it by sight and kind of pick a few points. And based on my order pair, it looks like y-axis symmetry. It's flipped across the y-axis, also called even. So we're going to go with C. Looks like it has y-axis symmetry. Okay, so it said that's not correct. Symmetric to the y-axis. Am I missing a part of this graph? Make it bigger. That's what it looks like if you flip it directly across. Choose all that apply. Oh, it also has x-axis as well. You could take every point above the x-axis and flip it below. So it's like two parabolas right across the middle. So this one has x-axis and y-axis. Okay. I didn't see all that apply. So there can be more than one, as I was showing, but this has flipped across the x-axis and across the y. Okay. So that should be what we need. Okay. Okay, they still don't like it. Does it have origin as well? This order pair? That would be hard to see. If you did a mirror image, what that would look like. Look like it has origin as well. Like I said, it's hard to kind of tell that. You can't really make a whole lot of order pairs. I guess we'd have to pick some. But, I mean, you don't have spots, so it's kind of hard to tell. I like to do it with functions. But we can see y-axis and x-axis pretty clear. Origin is a little bit hard to tell. Flip this up and then flip it over. Yeah, so it has origin as well. So think about kind of like flipping. If I go back to the image, that's the best way to think about origin. You take one part of the graph and then you flip it across the x and then flip it across the y. So that's what I'm kind of trying to get a mental image. So I'm just focusing on, make this big, focusing on just say the bottom half right here. So if I focus on this part and I flip it across, that's x-axis, and if I flip that across the y, that would match up with that piece, and it would work for every little section. So that's the image. That's what you need to mentally picture. So this is x, y, and origin, kind of like the circle. And with practice, you'll begin to get better at seeing those and understanding which one is which. So final check, and that is what we need.